see. Okay, delta H reaction. Okay, this just means the heat of the reaction or the enthalpy change. Okay, once again, so heat and enthalpy, a lot of times, I don't know why, when they came up with all this, they tried to confuse everybody, I guess, and use the terms interchangeably, and they don't just stick to one. Okay, so the delta H reaction, RXN, that just means for the total reaction, what the change is. So the change in enthalpy, but they also call it the heat of reaction, even though it's really the enthalpy. Okay, so if the delta H for the reaction is negative, okay, so if we have a negative delta H, this means that we have an exothermic reaction. Okay, so somebody even asked, I think it was 890 kilojoules last class, that when we looked at the diagram, why there was a negative there. Okay, and so that negative just says that that heat was lost by the system. Okay. If you have a positive delta H, then the reaction is endothermic because it is gaining heat, and so you have a positive delta H there. Okay, so how we would theoretically think that we could go about finding delta H of the reaction would be to take the, basically, I kind of look at it as this, the enthalpy of the final product minus the enthalpy of the initial reactants. Okay, so it's more like final minus initial, or you would look at the products minus the reactants. You would look at that enthalpy change, or you'd get the total change by taking final minus the initial. Okay, so how I think about this is just like, so let's say you had $1,000 in your bank account. Okay, this is what you had initially. Okay, after Christmas, you had $200. Okay, I probably have less than that. Okay, so if we want to find the change in our account, okay, we are going to take the final. Okay, so what do I have? What's in my account at the end? Okay, and what did I initially have? See, you relate it to money and everybody gets it. Okay, so our change is what? Negative 800. Okay, this is the same idea for the heat, or when you have this will be an exothermic reaction. So it's exo in your bank account because you lost it. Okay, so if we go back and look at these diagrams that we looked at on, take me just a second. I think I skipped it. Hang on. Yeah, I did. There we go. Okay. So this was the exothermic reaction. Okay, so our final, so if we actually had a value, so here's the energy right here. So here's our heat energy. So if we actually had a value here, okay, when we take the difference, it's going to be 890. Okay, so if we had a value here, you take your final value minus the initial value, and you would get a negative number. Okay, that's because your product is lower in energy than your reactant is. Okay. Okay. Experimentally, we're going to do this in the lab next Wednesday. Okay, we're going to find the delta H, the heat of a reaction, for two reactions. Okay. The problem is that we cannot, so if you want to highlight, I say this about probably 5 or 6 times through the lecture, is that we cannot measure heat. Okay, the actual symbol for heat, not enthalpy, is Q. Okay, so we're going to talk a lot about Q as well. Okay, we cannot measure Q directly. Okay, Q is the heat flow. It's actually a form of energy. Okay, so we can't just take and measure the heat of the react. It doesn't work that way. What we can measure is the temperature. Okay, and so experimentally, that's what we're going to do. We're going to measure the temperature. I mentioned this even last semester when we talked about heat, is that if someone goes over, I do it too, and I say the heat's on 72. Okay, technically, I should say the temperature is 72.1 or whatever it is over there, degrees. Okay, so our heat is the form of energy, and temperature is the measure of the intensity of the heat in the body. Okay, so experimentally, to do this, we perform a technique that's called calorimetry. Okay, and you're going to do this in the lab, so it's kind of a segue into that. Okay, and we're going to look at the temperature change. Okay, so just before we even move on, let's think about if we have an exothermic reaction, okay, and we're measuring the temperature of it. Okay, do you think your temperature is going to go up or is it going to go down? Exothermic. What's going to happen if you, so let's say we have water in our calorimeter, we'll see that in a second, and we add two reactants and they react, and they're exothermic. It's an exothermic reaction. What's going to happen to the temperature of the water? Better question. Temperature is going to go up, right? Okay, and then for an endothermic reaction, if the reactants absorb the heat from the surrounding water, what's going to happen to your thermometer, the temperature in your thermometer? It's going to go down, exactly. Okay. This is a very simple technique, and it is used, and I'll show one picture of what's actually kind of used in industry, but this is actually works very well. This is called the coffee cup calorimeter. We don't use coffee cups in the labs. We use a variation of that, so you'll see that on Wednesday. But basically, calorimeter means that you're going to measure the temperature, and you're going to measure the temperature of that is being absorbed, or the energy that's being absorbed or released. Okay, and so you're going to look at the temperature change. Oftentimes, for these reactions or for this technique, you want to have water is usually what's in the calorimeter. Okay, so that means that your reactants have to be able to react in water. So sometimes that can be an issue. Okay, so we're going to measure Q. Well, we can't measure T. So the second time I said that. Okay, and we're going to look at if heat is given off by the reaction, then the temperature, you guys already told me that, is going to go up because the water is going to absorb that heat. Okay. And then opposite. If the heat's absorbed by the reaction, then the temperature is going to go down and heat's going to be lost by the water. Okay, one more thing here. Okay, so, well, let me explain this. So we've got this beaker just kind of holding our coffee cup stable. So we've got this polystyrene cup and a cover. So what do you think the polystyrene is going to do? Okay, yeah, just keep it insulated. Okay, and make sure that no heat's lost out of the. If you have a leak in the system, then heat could be lost out to the surroundings. Okay, you have this glass rod or some variation that just has to stir. So you want to be sure that when you put the reactants in, so we're actually going to be hooked up to the computer, and we're going to have a temperature probe down in our calorimeter, but you're going to have it stirring. So you're going to have a stir rod in there because you want your reactants, they have to collide and mix in order for them to react. Okay, and then the thermometer is also in there. You want to be sure there's no leak here. And so if we think about if we place reactants in here, okay, so and it's an exothermic reaction. Okay, there are two things that are going to absorb the heat that is being lost. Okay, does anybody know one we've already kind of said? The water. Okay. But what else could absorb? Exactly, the calorimeter. Okay, this is our calorimeter here. So we have to know for each calorimeter, you have to know how much heat is it going to absorb and the water in order to know exactly how much was released by the reactants that you placed in the calorimeter. Does that make sense? Okay, so how we can go about doing this, you'll want to memorize Q equals MC change of T. So you'll have to use that equation. Okay, Q is for heat. Okay, do not get confused. Like I said, I don't know why they don't just stick to one symbol, but Q, uppercase, lowercase, or QP, all are for heat. Okay, that P just means at constant pressure. Okay, so these are all used interchangeably, so don't get confused if you look in your book and it's looks a little bit different. Okay, our units for Q. Okay, so we need to put this up here. Our units for Q, we'll go ahead and put our equation. Our units are joules or kilojoules. Okay, so we need to talk about each of these symbols here. Okay, Q is for our heat or heat flow. Okay, M is our mass in grams. Okay, so everybody should know what that is. Okay, C is specific heat. Okay, we talked about specific heat last semester. Didn't spend a whole lot of time on it, but if you've forgotten, you can go back and look. But I've kind of got the definition here. It's just the amount of heat required to raise the temperature of 1 gram of water by 1 degree C. Okay, what we do want to see here is that our units for specific heat are joules per mass times degree C. Okay, specific heat of different substances are known values, so they're given in tables for just about anything you can think of. Okay, so I will give you these values. You won't have to find them or memorize them. Okay, one that you'll probably get to where you memorize anyways is water, because we use that majority of the time. Okay, so the specific heat of water is 4.18 joules per gram degree C. Okay, for the third time, we can't measure Q directly, but we can measure its components. Okay, so if we think about this, if we want to look at or determine the heat that's absorbed by the water, okay, so Q of our solution, okay, which would be water so far. Okay, if we know the mass of the water, so we have 50 grams of water in the calorimeter, we can plug that in right here. Okay, if we know the specific heat, which we do, right, 4.18, and then if we measure the change of T, so that means we look at initially what our temperature is, and then we look at it afterwards, and we see the difference in the two, so we get our change of temperature. So if we plug in all three of these values, what do we find? Q. Exactly. And remember, Q, the units are joules or kilojoules. Okay? That will come important later. So we indirectly find a way to find Q. Okay, so I mentioned this earlier, but we're going to look at an exothermic reaction. Most of our reactions that are spontaneous are exothermic. We are going to look at some endothermic, so there are some. Okay, but if we're thinking about an exothermic reaction, okay, you guys already answered this earlier, so there's a reason for asking you what two things absorb the energy, the heat, in the calorimeter. Okay, the water and the calorimeter. Okay, so we have to know both of those values to be able to determine the heat that's released by the reaction total, right? If we just take into account the water, then that's going to be off compared to what in reality, how much heat is being released. Okay. These two terms in blue right here are the same thing, the heat capacity and the calorimeter constant. You will see both of those terms used interchangeably. I usually use calorimeter constant. I don't know why that one just kind of comes to my mouth quicker. But okay, so we have to know the heat capacity of the calorimeter. Okay, so when you go to lab on Wednesday, we're going to tell you what that is. So we've measured it already. Okay, but sometimes, whatever your calorimeter is, you may have to find that value. Okay, the heat capacity is the amount in heat. Okay, so joules divided by change of T in degree C. Heat capacity or calorimeter constant, joules. Okay. The units, you'll see in a few minutes we start calculations where most students make the small errors, and you have to really be able to know what you're looking for, I guess. So you'll see in a few minutes why the units are so important. Okay, so we've got to find the heat capacity. Okay, any ideas how we would do that? If I have this calorimeter and I filled it with water, I've got everything set up, how could I find out how much just the calorimeter absorbs?
Finding out how much the water absorbs.
Okay, that's a start. Okay. Okay, but what do I have to do? Okay, you're on the right track. Am I going to put reactants in it at all? Or am I going to just have the water in there? Okay, just the water. Why, do you think? Okay, very good. Okay, so what am I going to, if I find, what do I have to do initially? Y'all are probably already assuming that. What do I have to do initially? I've got the water in the calorimeter, initial temperature, but what do I have to add? Yes, I have to add a known amount of heat to the calorimeter, okay? So then you can subtract that known value from the value of the heat absorbed by the water, and that leaves you left with only the value for the calorimeter. Okay, so we're going to see that. Okay, there's numerous heat sources that you could use if you're asking. Is that what you're asking? Yeah. There's calibrated, just like, I mean, you guys add heat in the lab, but you don't know exactly the kilojoules, so it'd be a lot more expensive of what you have of a kind of a hot plate source that would calibrate and tell you exactly the amount of heat that you're adding. Okay, so we would add 3.425 kilojoules. Just theoretically, you could add a lot different numbers there, but okay, so we have to have this known value of heat that's being added to the calorimeter. Okay, but the calorimeter, like I said, there is only water is in there. We haven't added any reactants or anything to it. Okay, so the calorimeter contains 50 grams of water, and when you add that heat, the temperature goes from 24 to 36.54 degrees C. Okay. Now we're looking for the calorimeter constant or the heat capacity. Okay, so what are my units going to have to be in the end? Joules per degree C. Okay, and once again, I'm given the specific heat of water. Okay, the first thing, really all these calculations that I do is go as I find my change of T. Okay, so I take my final, which is 36.54, minus the initial, and get 12.54 degrees C. So that's my change of temperature. Okay, so the temperature went up, so it's exo or endothermic reaction? Exo, exactly. Okay. It's basically just a kind of a process of elimination here. So if now we have our change of T, we know our specific heat, and we know the mass of the water, so we can find the heat absorbed by the solution. So you may even want to, we're using QP, that means at constant pressure. You may even want to write Q solution, okay, so you don't get the two. You're finding the heat of the solution first. Okay, so we take our 50 grams of water times our 4.18. Okay, and also notice how all of our units cancel. Okay, so grams. Because remember, Q has the units of what? Joules or kilojoules, exactly. So you have to have your units cancel. Okay, grams cancel. And we can cancel our degree C there. Okay, so if we round up to 4 significant digits there, round down, we get 2,623 joules that absorb by the water, okay, absorbed by the solution. Now we're going to find the heat absorbed by the calorimeter. Okay, once again, heat has the the units of what? Joules, right. So if it asks for just the heat absorbed by the calorimeter, then you would stop here. Okay, so you take this value. Okay, where did this come from? Where did this number come from?
That was the very first thing you gave us.
Exactly. That's the known heat, yes, that is added to the calorimeter. Okay, it was given in kilojoules, so you can convert to joules. So you just move your decimal 3 places. Okay, and now you just subtract. So you take the heat put in initially, the value you're given, minus the heat absorbed by the water, and you're left with heat absorbed by the calorimeter. Exactly. Okay, but are we done here if we're asked for the heat capacity? Okay. Exactly. So we have one more step. This is probably the most forgotten step of this problem. Okay. So I just want to stop here. This is still the heat only of the calorimeter. Okay. So if we go one more step, all we have to do is divide by. So we take that 802 that we just got in step 3, and we have to divide by the change of T. And that leaves us with the correct units. Here we just rounded to 3 significant digits. Okay, so this is how you would find the heat capacity of a calorimeter. Okay. Any questions on this? Okay, so now let's think like we're in the lab. So had the calorimeter, we've done this, we have found the heat capacity of our calorimeter. Okay, so now we're ready to perform the reaction that we want to analyze. We want to see how much heat is given off or how much heat's absorbed by the reaction. Okay. All right, so I want you to take a minute before I even start going through this and just read this. Go through, think about what you're given, okay, where you might start, and think about what you're being asked. Okay. Did David come in? David McCauley? Hunter? If you don't have this written out or in some form can look, we're going to keep coming back to these values. So I would suggest you don't have to write the whole problem, but at least writing out the gist of the problem or the main values. So we'll be using a lot of these values for all of them. If you've forgotten Chem 111, they're going to quickly be brought back here in a few minutes. Okay, so I'm going to kind of talk through it step by step. Okay, so we have our calorimeter, and we have our acid-base reaction. The acetic acid, that's the first compound there, and sodium hydroxide. So we want to put this in the calorimeter and see what happens, see how much heat is going to be, released. So it's going to be exothermic. Okay, so if you were doing this or holding, when you add the two together, acid-base, it gets hot. So exothermic. Okay, so we have a solution. We have 25 mils and 0.5 molarity in AOH. Okay, so we don't just have grams. Here in a few minutes, we're going to have to go to moles. Okay, so you have to remember, we'll go over how to do that. Okay, our initial temperature is 23. Our final is 25. Okay, so you can go ahead. The first thing, like I said, I always do is find my change of T. Okay, we have 25 mils also of our acetic acid. We have 0.6 molar. So remember that uppercase M is molarity. That's for concentration. Okay, molarity is equal to moles per liter. or millimoles per milliliter. Okay. All right. We are given the heat capacity. Okay. So this whole step we just did earlier, we don't have to do that here. We're already given the heat capacity, and it's 27.8 joules per degree C. Okay, and we're assuming that the specific heat is the same as water. Okay, so whenever we have to plug in for C, and the density is 1.02. Okay, for the mixture as a whole. Okay, so when we mix these two together. Okay, the first thing we're going to do is we want to determine the amount of heat, Q. Okay, so what are our units going to end with? Exactly, joules or kilojoules. Okay, evolved by the reaction. And then part B, we want to determine delta H of the reaction. Okay, if we look over here, what's our units? Okay, so the only difference is the per mole part. So we have to add in a couple more steps to find moles. Okay. Okay, so going back to, this was already on a previous slide, but the amount of heat released by this reaction, we have to take into account the heat that's going to be absorbed by our calorimeter and by the solution, or the water here in our situation. Okay, so the first step is find change of T. Okay, so we took the 25.9 minus 23, 2.947. Okay, we know we're going to have to use the change of T in our calculations. Okay, I would star this step. This is one of the most forgotten as well, right here. Okay, we have to plug in heat absorbed by calorimeter, heat absorbed by the solution. Okay, the heat capacity is not the heat absorbed by the calorimeter because our units are wrong, right? We have joules per degree C. Okay, so you can't just take that 27.8 that you're given and plug it in for the amount of heat absorbed. Okay, you have to multiply it, so now your units will cancel, times the change of T. Of course, my iPad went dead. Okay. Okay, so our units cancel, degree C, degree C. Okay, 27.8, where did I get that number from?
That was the heat capacity of the...
It's what's given, okay? And we get 81.9. Okay, so we look up at the amount of heat absorbed by the calorimeter, 81.9 joules. Okay, so we have one piece here. Now we have to find the amount of heat absorbed by the solution. So we're going to use our Q equals MC change of T here. Okay, but we have to get to grams, right? Okay, because we've got mass. Okay, so you can't just plug in, 25 or 50 milliliters. Okay, so what you do is you take both of the volumes for your acid and your base, both of which were 25. Okay, so that gives you 50. Okay, then you multiply times the density. Okay, remember we used density last semester to get to a mass quantity. Okay, so now your milliliters cancel, and you're left with grams. Okay, so you have to go from milliliters to grams. Okay, because we're about to plug this in to Q equals MC. Okay, now we have our mass, 51. Now, go ahead and show that here. Okay, any questions on this? Or you're going to get to practice it here in a few minutes. Okay, so now we plug in our C, which is 4.18. I'll go ahead and do it over here, I guess, since I wrote it out. Okay, and then our change of T was 2.947 that we already found. so that equals 628 joules. Okay, so we found the heat absorbed by the calorimeter plus the heat absorbed by the solution. Okay, we find this by measuring the temperature, and then we plug it in to Q equals MC change of T. Okay, so now the heat produced by the reaction is 709.9 joules. So that is the answer to part A. Okay, because remember we're asked for heat. That means our units end in joules or kilojoules. Okay. For part B, we're asked for the change of reaction or the enthalpy change. Okay. The biggest difference here is this takes into account per mole, okay, of the reactants. Okay. So we're going to have to think and go back to our CHM112. Okay. We're looking for delta H reaction, joules per mole. So I have that in bold there, so you can. I think I even do that on the exam just to give you the hint of what your unit should be. Okay. Under the conditions of the experiment that we saw earlier. Okay, we have to determine the number of moles of the limiting reactant. Okay, then we're going to take that number, so don't forget our number here. So we're going to use this 709 because that is our joules, right? So for our delta H, we're going to have 709.9 joules over moles. We just haven't determined the moles yet. Okay. Okay. Anybody remember what a limiting reactant is, or have any idea how we're gonna find it? Anybody? First off, what are our reactants? Acetic acid and the NaOH. Okay. What do we know about those two? What do we know about them? If you look back at the problem. Okay, we don't know the moles. We know the molarity and the, well, we kind of know the mass, but we know the molarity and the volume, right? Okay. Molarity equals moles over liters, or millimoles over milliliters. If we rearrange this, we get molarity times liters equals moles, or millimoles. So if we use molarity times milliliters, we get millimoles. Okay. Okay. If we were given grams of the two reactants, then what would we do to get to moles? Just convert from grams to moles using the periodic table, adding up the formula weights for the compounds, and there you go. Okay, so what we're going to have to do, okay, here's our reaction. So at the very top here, acetic acid, just showing you that again. Okay, what's our ratio of acetic acid to NaOH? Okay, 1:1. Okay, we have 25 mils of both. Okay, so you start with your volume and you multiply it times the molarity. So you look back at the problem, it was 0.5 molarity, which molarity is equal to millimoles per milliliter. So that's where these units come from. Okay, and if I hadn't gone dead over here, then I'd be able to cross these out for you. Okay, but milliliters cross out. Okay, when you're finding a limiting reactant, okay, you can do this two ways. This is actually the long way, and I'll show you the short way here in a second. Then we want to look at a product. So we picked a product. So we have this sodium acetate right here. And we want to pick a product because we want to see which one are we limited by. Okay, so if we look at our product here, we still have a 1:1 ratio, right? Okay, so we have 1 millimole of NaOH for 1 of the sodium acetate. So we get 12.5. So all we did was multiply times 1. Okay. Did the same thing here. So 25 times 0.6. This was given to you in the problem. Okay, times 1 again because we have a 1:1 ratio. Okay, and we get 15. Okay, so we are limited by not trying to trick you because I'm pointing at the wrong thing. But what's our limiting reactant? NaOH, right? Okay, a lot of students accidentally will put this. That's your product that you're trying to see how much you can make with that specific quantity. Okay, your limited reactant is over here. Okay, remember your reactants are NaOH and the acetic acid. Okay, how I actually do this, so it depends on whatever works for you. I don't actually do this third step. Okay, I stop at this value here, and here in a second you'll see why I do that. It prevents an error that is usually made in the next step. Okay, and then I just compare the two. Here I have a 1-to-1 ratio. So whichever one's larger or whichever one is smaller is going to be my limiting reactant. Okay, and whichever one's larger, I'm going to have an excess. Okay, but if let's say that we had I'm just going to pretend here, we have a 2 to 1 ratio. Okay, and this wouldn't happen because the equation doesn't balance, right? But we're just pretending here. Okay, and we did this first step. So we got 12.55 and we got 15 here. So we won't do this step here. Okay. All right, so which one would be the limiting reactant? Okay, so I do this first step, okay, and then all I do is go back to my equation, and I say, okay, I need twice as much acetic acid than I do NaOH. So I'd look over here, say, okay, I got 15 versus 12. I don't have twice as much, so this is my limiting reactant. If it's a 1-to-1, it's easy, okay, but the problem is the last step. Okay, so here we found our millimoles, okay, and we plug that in. The last step, I promise. So this is our 709 that we found earlier, and now we plug in the moles. Okay, we had millimoles, so you just need to convert it to moles. Okay, and that's 0.0125. Okay, the number that goes here, you'll see this on the practice test. This is actually the most missed of the whole practice handout, is this right here. Okay, this number is the moles of the limiting reactant, not the product. Okay, even though it didn't matter here, right, because we had a 1-to-1 ratio. So it was 12.5 whether or not we stopped here or went to here. Okay, if you don't have a 1-to-1 ratio and you do it this way, you need to go back here and look at how many millimoles you found of the reactant, okay, not of your final product. Yes, if you can do it, see it that way, it just prevents error, because the number you get right here is the number that you use in the next step.
Oh, okay.
Do you get what I'm saying? If you do this step, and let's say this was a 2-to-1, you're going to get another answer here, and that's not the number you plug in the next step. Okay, this part is confusing. You'll see this in the handout here in a few minutes. So I'm just trying to warn you before this happens. Okay, so the number that goes here, we had a 1-to-1 ratio. So it looks like you just plug in that last number and that's that. Okay, but when you have a 2-to-1, 3-to-1, 4-to-2, whatever it is, okay, the number that goes here is the moles of the reactant, not the product, if you choose to do those two steps. Okay. So, but we'll go over it after you go over the work on the handout. Okay. Last thing just to show, this is what they used to use a lot in industry, but hence the word bomb calorimeter. You can imagine that this is not very safe and is not used a whole lot. There's some stuff about this in your book. I don't really go into detail because, like I said, this is pretty much used very limitedly, because you can imagine here, so you've got this, it looks similar really to just your coffee cup calorimeter. The difference is it's, of course, a much larger quantity. You have a vast amount of water to soak up the heat that's being released. Okay, you basically have this steel bomb here. Okay, so you place the sample in the dish, and then it's insulated. It's not just your, polystyrene cup. I mean, it's super insulated. But you can imagine, it's got your stirrer, your thermometer, all that. And they used to use this a lot in industry. But you can imagine what if you don't calculate right, or if you don't take into account, especially a new reaction that you don't know how exothermic it is, that you might not have enough water in there. And so if you don't have enough water or insulation, you can imagine that's why it's given the name bomb. So not very safe. So okay, now I want you to work on your handout. So it goes through kind of step by step what we just did. The first reactions are for finding the heat capacity. So going back to the very first calculation that we did. Okay, and then you're given a reaction, and you go through and find the heat and the delta H for it. Okay, are there any other left over? I don't think. I didn't print tons of them. Does anybody have the handouts? Or did we run out of them already? Okay. Here, I'll pull it up from Blackboard. You guys just tell me, those of you that don't have one, Andrew, I've got it up here. If you want to, just tell me to scroll down when you're ready.